all very interesting short talks.
Yep.
And we start with Morrish talking about a signature-based algorithm for solving the inverse problem with discretely observed trajectories. But you'll explain that it works.
Yeah. Hi everyone. I'm Tom. Yeah, I realise it's quite a broad crowd today, so I'm going to try and cover a lot of bases with the risk of making no one happy or making everyone happy. But let's see. So the motivation for this originally, when I started the PhD, was animal movement modelling, and we kind of thought it'd be nice to try and mix the areas of rough paths with the movement of animals, because it was something that hadn't really been done yet. So here's two examples of what an animal path might look like, plotted on top of a map. On the right, we've got a zebra moving across a reserve in Africa, and on the left, we've got an elk traversing up a mountain in Antarctica, Alaska. The common model for both of these animals that we used is some kind of variation on a Brownian motion. But as you can see from that they don't really have the same diffusive kind of pattern scaling limit in the random noise driving them. And you can see that if I just plotted the latitudes of both of these animals, or different types of animals, on a time series. So both of these are dates and time series at regular sampling intervals of the zebras on the right and the elks on the left. And instantly you can see that to model both of these with a Brownian motion might not be the best idea. So what are the two common approaches? So one approach is you could either specify, so the most used kind of process for these animals when they're foraging around a home location, so they have a spot where the bed is and they would disappear off and come back to that home location, is to use the Ornstein-Uhlenbeck, which makes sense. But how would you specify that? So one idea is to specify it on their location, which enables you to give an exact home location in the model. That's too rough, as you can kind of see from the bottom left plot. That's the Brownian motion in 2 dimensions, the Ornstein-Uhlenbeck. So one kind of method that's used often is to integrate, so specify the model instead on the velocity of the animal, and integrate that to get the location, which gives you a smoother path. However, you then lose some of the biological understanding in the parameterization. So originally I kind of thought we could use a fractional Brownian motion instead. So if you use a fractional Brownian motion in your driving noise, as you do in the bottom right-hand side, you get something that looks a little bit more realistic for the movement of an animal. There's also the possibility of changing your H parameter to make it smoother or rougher, depending on the animal. But we're going to look at a more broad class of equations because this is actually not so hard to solve as we saw earlier with Young integration. Okay, so the setting that we're going to be talking about is that we're going to observe, just like we do in the animals, we observe the response to a rough differential equation at discrete and irregular time steps. This is kind of like the most common real-world setting you can get, right? Continuous processes going through time, and you sample it irregularly. You never observe the continuous trajectory. So our rough differential equation looks like that. Some rough path lingo here. Xt belongs to geometric rough paths with p variation. M dimensions in real numbers. The reason that is so that you can approximate it well in a bounded variation sense, so that when you take the limit in p variation, it converges to the rough path. To join that up with some of the talks we had earlier, the fractional Brownian motion is in that category when h is greater than a quarter. Things get tough when you go less than that, so we're going to stay in that world. Solutions also are in that world, and they exist. We're not going to get too much into the theory, but essentially we're in a nice setting here, okay? We can also simulate from this model. We're not going to talk about exact simulation today. That is an equally hard problem with these types of equations. But we might not know the parameters. We may need to do inference on them. A second motivation for this work is this type of SDE, which is where, so not this type of SDE, is a complex type of SDE where you can't make it reducible. Okay, and a reducible SDE or a commutative one is where you can take some kind of transform of your response, yt, that allows you to write a new SDE that has a unit coefficient in front of your as your diffusion coefficient. If you can do that, you can perform far easier inference on these kind of things because your solution becomes far easier to gather. So we're going to try and work on things that aren't like this. So some irreducible examples are this model for flocking, where you have some kind of velocity term which has a difficult diffusion coefficient that depends on more than just the variable that you're looking at. Okay, so if this is animal I that's moving around with velocity t, the velocity of that bird, say in a flock, will also depend on other animals in the flock in a way that doesn't just affect the drift. That's a classic example of something that's irreducible. I.e. that in Ito calculus there is no transform that you can write a V that would render this into a unit coefficient in the diffusion. Another example of this in multiple dimensions is the Wright-Fisher diffusion, which is a really classical equation from population genetics. Not really my interest, but lots of people are interested in that. These things, another important thing to say is this only happens in multiple dimensions, because if you're in a single dimension, you can take 1 over the variance and integrate it, and that gives you your transform. So we're in multiple dimensions here. Yes, so the rough idea, that's my idea of a pun. What are we going to do? We would like to find a path, x delta of c of y, such that, so this is for the driving random noise in a sense, it's calibrated to the data, i.e. when you put it through the model that you want to put it through, say the flocking model or the Wright-Fisher, it joins up with your data points that you observe from your real-world system. The parameterization you put on that will not be the exactly same parameterization that you are talking about. So it's not going to be the continuous fractional Brownian motion. It's going to be an approximation of that in discretized time, such that it converges to the right one in p variation. That ensures that the solution that approximation drives in the limit also converges to the right continuous solution. And this is all in rough path sense as well, so the lifts converge as well, which is what the p-variation bit does. Okay, so there's some pictures of kind of what I mean there. So there's some underlying real process here, xt, true driver, that goes through this model, which we write I of theta, it's the Ito map. You get some response, y, that you sample discretely and potentially irregularly at these red dots. We then put some kind of parameterization on x in discrete time, which means that we can solve those integrals and go back to x so we can go back to y in the right way. Yeah, so the discretization that we're going to use is a very simple one. It's piecewise linear paths, but you could use any kind of discretization here that makes sense, so that it converges to the right rough path in the limit. Okay, right, so we have a signature-informed algorithm that we're going to use to do this. I'll be honest, I thought I would not be the first person to really go into detail on the signature today, so I took out this slide this morning and then put it back in about 20 minutes ago. I'm going to give a really brief overview, and then because it's kind of important for the next part. I'm sure you'll hear far more about this tomorrow. So the signature of a bounding variation path is essentially just a kind of summary of that path. It's a data reduction technique with continuous paths, and it's the set of iterated integrals. If we want to think about this in what is that actual vector of numbers, the first level is how far the path moves away from its initial point. So where does it end? Displacement. The second level is the Levy area. Well, the second level summarizes the Levy area, which is the area that's caught if you drew a straight line from the beginning to the end of the path, modulo with some translation. The useful property so if you go on to further areas, you start to capture more and more iterated areas that summarize different parts of this. The useful property of this, thanks to Horatio and some others, is that this signature, this infinite tensor, uniquely defines the path that it summarizes up to time reparameterizations, if we speed up the path or slow it down, and tree-like additions. Now, tree-like addition is where you jump from the path up to a point and then directly retraverse that exact same path back to it, which doesn't happen in the real world. So if you want to get rid of tree-like portions, you add time as a dimension in your path, because obviously you can't retrace time. Okay, so when we do our iterations in this algorithm to go back to this kind of piecewise X that drives the points that we see, i.e. is consistent with the data and the model, we're going to try and keep that signature uniqueness in mind. So when we make changes to our Y, our response, we're going to make sure that the signature doesn't change. So how does this work? We initialize with our X path at 0. We iterate it by putting the path through the model. This is our piecewise linear path, which initially is set at 0, to get a new Y path. We then correct using that property that I just mentioned about the tree-like uniqueness by, at the sample points that we sampled the real data, connecting that Y path up to the points and drawing back down to the original Y path and reparameterizing time around that step. So it's got time to jump up and back. That doesn't necessarily make too much sense from doesn't intuitively make too much sense to do that, but it does in the sense that it will converge in the right p-variation limit because the signature is invariant to that. Okay, and then we reverse that again, so we now have a new Y path, and we put that back through the Ito map, but the inverse step, to get our new X, and then we project onto the space that we're looking for, which is the piecewise linear X. As Peter mentioned earlier, because we're in this piecewise variation approximation, we can say this is essentially solving a set of ODEs, where you're calibrating the solution to the ODE to be the right thing that makes sense with the sample points. Right, so what have we added to this algorithm to make it a bit better? To update this algorithm, you need to integrate your inverse f over the correction. So that little bit of the path that joined up with the sample points, you need to evaluate that f over that linear path. To make that slightly easier, because that's not going to be a closed form integral most of the time, so in this simple case, you get something that's quite tough to do. So you can correct your path in a slightly nicer way. So one of those ways of doing that is using a splitting algorithm. This is where you correct each dimension of your path in turn and come back along it. It's still tree-like, it still retraces the plot, and it still has in fact, it's exactly the same solution, but it's far easier to solve that integral. So this is kind of the inverse version of splitting. Some people might have seen the forward version of splitting when you're trying to simulate SDEs. Okay. Reducibility. So that commutativity condition essentially means that the increments of y, the path that you see, can be uniquely described by the increments of x, and there's a one-to-one map of those two things. Therefore, this algorithm converges in almost one step when you've got a reducible dimension in your multivariate SDE. So you can also remove all of those from your algorithm after the first step. So both of those things allow you to A, get exact solutions, and B, speed it up. So again, we've tried to develop this so that it can be used with most models, like a lot of models from the real world. So kind of just had fun putting it on a bunch of different models at this point. Here was one, which is opinion dynamics. So this is the dynamics of a person in a crowd where you can imagine that your political opinion might drift according to the people closest to you. Where I added a scaling term to make it slightly harder on the diffusion coefficient. And then you observe some of those people in a population at discrete times. So that's an example of what the dynamics of this might look like with 100 people. We observed 20% of them, so 20 out of 100. So the results of this algorithm, the nice thing about this algorithm is because you're using the signature, which is a global representation of the path, you're correcting the entire path in one step, in a sense. You're moving one up, which affects sample points later on. It's not local in the sense that you don't, in the Newton-Raphson approach of solving these ODEs, you'd need to calculate the error of each interval and then stack them up. So this globally corrects it. So we can kind of consider this against the local Newton-Raphson approach. Here we've changed the number of observable paths and the dimension of the process. And yeah, it's pretty clear that it does very well when you've got more dimensions and you observe fewer of them. And that's because that's where the simulation of the model becomes the most important point, rather than the knowledge of it. When you have more knowledge of the model, then something like a Newton-Raphson, which develops gradients, will be better than the signature, because you don't do that in this case. You really take a very first-order approximation. In another model, where we wanted to use some fractional Brownian motion, because that's what we were talking about earlier, this is just an obvious square root model where you have some level of irreducibility. The reason it's irreducible is because there's a y2 in the top diffusion term. And the nice thing here is that it converges in the same number of iterations regardless of your sampling rate. There is some computational error on the distance in the bottom left, which is the difference between higher sampling rate and lower sampling rate, but it converges around the level of 15 iterations. And that same effect happens with your roughness. So it's kind of uniform in seems relatively uniform in roughness and in sampling rate. Again, the difference there is due to computational error. Okay, and the kind of original rough idea thing that this converges to the real solutions in the p-variation limit is justified here, where if you take an actual SDE and simulate it exactly using a really expensive algorithm, the solutions that we get if we take a finer and finer discretization converge to the real ones in phi variation, which is exactly what we want. Yeah, cool. So that's pretty much me done. I just wanted to say sorry to all the organisers for submitting this all very late. I've had my own animal movement problem at home. It's very lucky that I've got a talk to present today, because yesterday my laptop was in his mouth for about 5 minutes and I was shouting. So yeah, apologies for all the delays. Thank you very much for listening. There's some references. Yeah.
Questions?
Actually, a kind of more conventional approach for reproducing, say, the path of a foraging animal or something is that you rather look, say, at probability distributions of, say, velocities and correlation functions, and then you plug this into your favorite stochastic model, and that way you reproduce the path. Actually, I'm going to talk about that tomorrow.
All right, cool.
And obviously, your approach is very different in that you really look at the roughness of your path, so more microscopically. Therefore, my question is, how well does your approach then reproduce these statistical quantities that typically you're after, like mean square displacement and correlation functions?
Yeah, I mean, that's kind of another talk, because a kind of sister project to this is likelihoods stuff, so developing likelihoods for these parameters. It does quite well, and not as detailed, but more efficiently. And far easier to explain and solve. I will come back one day and give another talk on the likelihood, I'm sure.
It should do well because it's more microscopically based in some sense, but it's still not obvious to me under which precise conditions.
Well, the nice thing about it is that you can split the probability in some sense, because you can deal with these things pathwise and then put the probability at the end. So this really applies for any Gaussian process that you could approximate with a bounded variation path.
Probably require avidicity or something like that to make it work, right?
Potentially, yeah. Potentially.
Otherwise, because you're going along a single path, then for...
Yeah.
Okay.
Yeah.
Yes.
So going back to the sort of motivating example on animal movement, there's a whole class of models that are used for that, where, as well as the sort of short-term dynamics, there's some sort of underlying discrete behavioural state, and so you get essentially segments of the path with different properties. I'd just be interested to know whether you kind of thought about that, or how it might apply.
That was where we started trying to do that, and it got quite hard quite quickly. Specifically with these fractional Brownian motion examples, I really want to go back to it. That's kind of what I want to do. We'll get there. State dependence. So you have some underlying Poisson process or something, right, that jumps the behavioural state. So my dog jumps from biting my laptop to sleeping at some rate. We would like to do that for sure, but not yet.
Thanks.
Thank you.
All right, thank you.